This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about shear stress distribution in various sections. So in the previous session, already we have discussed about distribution of shearing stress in rectangular section, circular section, triangular section, and then high section. Now, in this today's session, so I want to discuss about distribution of shearing stress in T section. So first we will see the outcome of this topic. At the end of the course, the student should be able to analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. Whenever the beams are subjected to various loading, so how to distribute this shear stress across the section. So after completion of this module or topic, the students should be able to analyze all these things like theory of simple bending and then distribution of bending stresses across the section. So first of all, introduction about distribution of shearing stresses already you know. So once again recall the shearing stress distribution introduction part. We have obtained a relation which helps us in determining the value of shearing stress at any section of a beam. So already we know in the previous sessions already we have derived one equation, that is a shear stress equation, that is force multiplied with A by IB. So this equation already we have derived. This we shall study this the distribution of the shear stress along the depth of a beam. So for doing so, we shall calculate the intensity of shear stress at important sections of a beam and then sketch a shear stress diagram. First, we will calculate the intensity of shear stress at important sections of a beam and then sketch a shear stress diagram. So, such diagram helps us in obtaining the value of shear stress at any section along the depth of the beam. So, now we shall discuss the distribution of shear stress over the following sections. So, already we have completed the rectangular section and triangular section also completed and circular section. And I section also in the previous section I have discussed. So now in this section, we will see the T section distribution of shearing stress. So the T section also same as I section. So once again the I section details we will see, and then we will enter into T section shear stress distribution calculation problem we will discuss in this today's session. So first of all, the distribution of shearing stress over an T section. The procedure for determining the distribution of stress over a T section is the same as discussed for I section. Whatever you have discussed in I section, the same procedure you have to apply for this T section. So in this case, since the section is not symmetrical about x-axis, therefore the shear stress distribution diagram will also not be symmetrical. In previous case, in I section, the distribution of shear stress is symmetrical. Why? Because the I section is symmetrical about x-axis. See, section. So, symmetrical about x-axis. But in the case of T section, not symmetrical. See? So that the stress distribution also not be symmetrical. This is I section. This one is T section. So detailed procedure, once again we will see. The distribution of shearing stress over I section. So same procedure also apply for a T section. But only difference is in T section not included this planes portion up to here only. So that the stress distribution diagram also obtained up to here. So the width of this one is planes and the web. In T section also same names. And dimensions shown here B, width of the web and depth of the web, and from here to only D, capital D. So you know this one is neutral axis. So the B is the overall width of the section, overall capital D is the overall depth of the section, and the small d is the depth of the web. The small b is thickness of the web. We know that the shear stress on a layer JK at a distance y from the neutral axis is shear stress is equal to F into AY bar by IB. So already we have derived in a previous session. So in this, in I section, I will discuss about two important cases when y is greater than d by 2 and y is less than d by 2. See in this, the small portion you take, same in T section also take like this, the JK. But don't consider this one only up to here. Then in T section, not included. See, so here the d by 2 and capital D by 2, the distance of the section from its neutral axis. This is y. Now, we need to calculate the center of gravity point from its neutral axis, that is y bar. It means the y lines is the plane as shown in figure. In this case, the shaded area of the planes, the area is b into d by 2 minus y. In T section also same. The area is b into d by 2 minus y. And y bar, y plus half of the distance. So now, substituting these values of a and y from the above equations in our original equation, one of shear force. So that is, this is shear stress. Shear stress is equal to F into A y bar by IB. What is A? A is P into d by 2 minus y, and y bar, y plus half of the distance, that is d by 2 minus y by IB. So in this case, the I is equal to BD cube by 12 for rectangular section. Clear? Thus, we see that the shear stress increases as y decreases. So we also see that the variation of shear stress with respect to y is a parabolic curve. So it means the upper edge of the flange where y is equal to d by 2, the shear stress is 0. And the lower edge y is equal to d by 2, the shear stress. So substitute the y value in this, you will get F by 8I into capital D square minus small d square. Similarly, when y is less than d by 2, less than d by 2. So in same in I section, whatever you calculated, same procedure apply for T section also. So what we have did in this I section, first we have calculated y is equal to greater than d by 2, and then shear stress calculated F by 8I into d square minus capital D square minus small d square. And the second point is when y is less than d by 2. So it means that y lies in the web. So in this case, the value of y bar AY for the planes. So that is AY bar is equal to B into D by 2 minus small d by 2 into d by 2 plus half of the d by 2 minus d. So finally you will get capital B into small capital B into capital D square minus small d square by 8. So and the value of AY bar for the web about JK. So this one also we have calculated. So in last session already we have completed this I section. So AY bar is equal to capital B into d square capital D square minus d square by 8 plus b by 2 into small d square by 4 minus y square. So you know here capital B is the width of the planes and d is the depth of the web and small d is the depth of the planes. And y the distance of the JK portion small elemental section portion from its neutral axis. Now substituting the value of AY bar from the above equation in our original equation, you will get the shear stress. The original equation shear stress is equal to force into AY bar by IB. So now the by IB is equal to B into capital D square minus small d square by 8 plus B by 2 into small d square by 4 minus y square. Thus, we see that in the web also the shear stress increases as y decreases. We also see that the variation of shear stress with respect to y in the web also is a parabolic curve. So at a neutral axis where y is equal to 0, the shear stress is maximum. So substitute the y value 0 in a shear stress equation, you will get the maximum shear stress. So substituting this y, you will get the shear maximum. And the shear stress at the junction of the top of the web and bottom of the planes also calculated. Substituting y is equal to d by 2. So you will get by 8i into capital B by small b into d square minus small capital D square minus small d square. So this is the procedure already we have followed for I section. So up to here, we have discussed about I section. Already we have covered in a previous session. So once again, recall the procedure. Same procedure apply for the T section calculation, the shear stress distribution calculation. So now we will see the T section shear stress distribution, how to calculate over and T section. We will see through this problem. The T-shaped cross section of a beam shown in figure. So I will show you the diagram. Is subject to a vertical shear force of 100 kilonewtons. Calculate the shear stress at important points and draw shear stress distribution diagram. So moment of inertia about the horizontal neutral axis is given 113.4 into 10 to the power of 6 to the power of 4. So here for this T section, whatever you followed in I section procedure, calculate the shear maximum shear stress at important points of this of the T section into AY bar by I into B. So for this, first need to calculate AY bar. and then the already force given, and I, uh, BD cubit wall for rectangular section, and B is the dimensions given in the figure, and according to the given dimension sections, we need to calculate. See, in this the given cross section is T section, so the shear stress is equal to, that is 100 kilonewtons. Sorry, shear just force, not shear stress. The shear force is 100 kilonewtons. So converted into newtons. And the moment of inertia, the moment of inertia also given about neutral axis 113.4 into 10 to the power of 6. The first of all, let us find out the position of the neutral axis. So that is A y bar. So what is the position of neutral axis from its center of gravity? We know that the distance between the center of gravity of the section and the bottom of the web. So first given section divided into two portions, one and 2. So this is flange and this one is web. See, the dimensions are given in 200, the depth of the web portion, and the depth of the flange is 50 and width of the flange is 200. And this point is the center of gravity, distance between the center of gravity of the section and the bottom of the web also given, that is 87.5 from here and minus 50. So we will get the dimension. So first calculate the y bar. How do you calculate the y bar? The center of gravity. A1 y1 plus A2 y2 by A1 plus A2. So what is A1? A1 is the area of the section, area of the first section. And A2 is the second section. So y1 is the distance from its, the distance of the section from its neutral axis. Similarly y2. So A1 is 200 multiplied with 50. So breadth, depth and that is B multiplied with D. So we will get area. So now 200 into 50 multiply with 225. So why? Because the distance of the section from here to here, this is y1. So 200 plus 50 by 2, 25. So 225. And similarly A2, 200 multiply with this section. So first section, number 1 is 200 and 50. And this one, 200 and 50. So this is second section and first section. And then area calculated and substitute in this, we will get 162.5. So that is they were already given in this section 162.5. So distance between the center of gravity of the section and the top of the flange, what is the distance? 200 plus 50 minus 162.5. The 200 plus 50, 250 minus the 162.5. So you will get the distance between the center of gravity of the section and the top of the flange. So that is 87.5 mm. We know that the shear stress at the top of the flanges is 0. There is no shear stress in the top flange. Now, let us find out the shear stress at the junction of the flange. The junction of the flange and the area of the flange of the section. We know that the area of the upper flange is 200 into 50. The y bar for the flange of the flange and the web, the flange at flange junction 87.5 minus 50 by 2. So that is 62.5. We will get the width 200 mm. So shear stress at the junction of the planes. Now calculate flange and web. Apply this original equation. Shear stress is equal to force into A into y bar by I into P. So what is the force given in the problem? 100 kilonewtons. Substitute. Area already you calculated. That is 200 into 50. And y bar also you have calculated 62.5. What is the I? The moment of inertia given in a problem. 113.4 into 10 to the power 6 into the width of the section, the flange, that is 200. So finally, you will get 2.76 megapascal. So the shear stress at the junction suddenly increases from 2.76 megapascal to 2.76 into 200 by 50, that is 11.05 megapascal. The shear stress at the plane is 2.76 and then increases to 11.04. So now let us find out the shear stress at the neutral axis where the shear stress is maximum. So considering the area of the T section below the neutral axis of the section, that is AY bar is equal to 162.5 multiplied with 50. 162.5. From this only this second section, web section. From it's 162.5 and this one is 50. So we will get AY bar is equal to 660.2 multiplied with 10 cube. So the maximum shear stress, force multiplied with AY bar by IB. So the shear stress, shear force given and the area calculated, and you will get 11.64 megapascal. So the distribution of shearing stress over an T section is 200, width and depth is 50. The section depth of the web is 200. So now draw the shear stress over a T section. So already we have calculated here up to planes is 2.76 and then web portion up to here they suddenly increase it to 11.04. So this is maximum shear stress. So here, see the shear stress distribution drawn in T section. So like this, you need to calculate the shear stress distribution in T section. So here, same procedure we have followed, whatever you have discussed in I section, same procedure here also need to apply for this problem solving. The maximum shear stress occurred at this portion, so F into AY bar by IB calculate. So area of this T section. So below the neutral axis of the section. Clear? Below the neutral axis of the section up to this one. Calculate obtained the 11 point. So the first one, in case shear stress at the junction of the planes and web is 2.76. So that the suddenly increases to 11.04 megapascal. Clear? So here calculated the 11.64 megapascal shown, and then so now draw the shear stress distribution. What he has asked in a problem. So first you calculate in problem. Calculate the shear stress at important points. So already we have calculated at the planes and below the junction portion of the plane and web, and also web portion you have calculated, and then draw the shear stress distribution diagram. So that already we have drawn in I section. Clear? So in I section already you know the shear stress distribution. I will show you this one. The shear stress distribution. So in planes and junction also calculated, and then in web portion also. So only in this I section there is no bottom flange. So that the shear stress occurred in this T section at various points already calculated. So according to the calculated values, draw this diagram. 87.5 already this one. The stress is shear maximum is 2.76, and then this one also 11.04 shear stress at the junction, and then at this portion from its neutral axis below the neutral axis, that is 11.64. So it is increases. So that the maximum shear stress occurred at this web portion. See? So like this, how to calculate the shear stress distribution in various sections. The references: S. Ramanamurtham. The title of the book is Strength of Materials. Publishers are Danpathy Rai. And R.K. Rajput. The title of the book is Strength of Materials. Publishers are Chand and Co. And R.K. Bansal. The textbook is a textbook of Strength of Materials, Lakshmi Publications. And R.S. Kurmi and Gupta. The title of the book is Strength of Materials. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.